are different types of aqueous solutions. Two that we're familiar with from just regular life are salt water and sugar water. So salt water, like the ocean, or you take a cup of water and you put some salt in it. Maybe your mom told you to gargle with salt water. Salt water is just a homogeneous mixture of sodium chloride and water. Sugar water, which basically is what most of our beverages are, just with some flavors and colors added, is a homogeneous mixture of sucrose and water. When you stir either of these, and they look very much alike, salt and sugar look alike, they're white crystalline solids. You stir it into the water and it seems like it's disappearing, right? But it's not. We can tell by tasting the water that it's still there. Well, how does that happen? How does salt dissolve? How does it disappear? How does sugar dissolve in water? When a solid is placed in a liquid, there are some competing forces. So here the purple is representing our solute. This is a solid, they're touchingly close. And there are interactions between these molecules or ions, whatever these particles are, that keep them together. That's why it was a solid in the first place, because the particles are attracted to each other enough that they're not going to fly off into the gas state or even melt on the counter. But now this solid is coming into contact with the solvent, and so there's a new kind of molecule around. And so there are going to be interactions between the solvent and the solute molecules. And we also have interactions between the solvent and the solvent molecules, which, they didn't show that one on there. That would be between these guys. That's solvent. And so whether this solid will dissolve or not depends on the relative strengths of all those different forces. If the forces of attraction between the solvent and the solute are strong enough to overcome the interactions between the solute and the solute molecules, then the solid can dissolve. So, it's like this one coming over, hey, come out and play with me, right? Well, I really like these guys. Well, how much do you like them? Right? Do you like them so much that you're not willing to go out and try new things? Well, then you're not going to dissolve. But if this attraction is greater than the attraction to stay with your little herd here, then this can go off and play, and the solid can dissolve. So what are those kinds of interactions? We're going to talk about them very briefly here and then more in depth in a later chapter. This is an illustration of a water molecule. So this big one in the middle, that's the oxygen, and then these two on the side, those are the hydrogens. Water is held together by covalent bonds in which the electrons are shared between the hydrogen and the oxygen. So sharing can be even, 50-50, and sharing can also be not quite so even, right? Like big brother sharing a cookie with little brother, it's like, well, I shared the cookie, but I took the big half, right? Or you're forced to sleep with your sibling because you're on vacation and there aren't enough beds, right? And what happens with that blanket, right? Somebody always gets more of the blanket. Uneven sharing. So there's uneven sharing of electrons here. Oxygen hogs the electrons. So the electrons that are being shared between these two atoms are going to be more on the oxygen side of that bond. And that'll be true over here as well. And so that makes this end of the oxygen molecule a little bit negative, and the hydrogen ends a little bit positive. That's a delta, a lowercase Greek d. So it kind of looks like a D that's got a problem with its posture. It's all slumped over. So this is delta. And this is a partial charge. So it might be like 1/10 of a charge. It's just a little bit of charge. when we put sodium chloride, table salt, into water, we have sodium ions and chloride ions, and those are attracted to each other by those ionic bonds. The positive and negative charges attract each other very strongly. But the sodium atom is also going to be somewhat attracted to the negative end of water molecules. Now, this is a full -1 charge over here, and this is only a partial negative charge. So it's going to take more than one water molecule to make up for the attraction to the chloride. The chloride has a negative charge. It's attracted to the positive sodium ion, and it's also attracted to the positive end of water molecules. And so what happens is something like this, where a bunch of water molecules will come and surround the sodium ion, replacing the negative charge attraction that it had for chloride. And for the chloride, a bunch of water molecules are going to come around it, but they're going to turn the other side, and so they're going to make up for that loss of the attraction that it had with the sodium ion. So it's, this analogy can go in all kinds of weird directions. I'm going to try Pinocchio this time. Do you guys know the story of Pinocchio? Little puppet who wants to become a real boy. But then if he lies, his nose grows, right? And he got into a whole bunch of trouble because these friends came and enticed him to go off and do bad things, right? So these guys are like Pinocchio, and all these bad influences are coming around saying, hey, come on out and play with us. This is better than the child stalking analogy, believe me. So as a result, we have these ions that are able to float around. They're not going to get stuck to other ions because they're happy with this surrounding of the water partial charges. Does that make sense? So we said we were going to talk about different kinds of solutions. Here are two kinds of solutions: electrolyte solutions and non-electrolyte solutions. So electrolytes are substances that will dissolve in water to form a solution that conducts electricity, electrolyte. And so this category includes all soluble ionic compounds, because when ionic compounds dissolve in water, they separate into ions. One of these days, I'm going to get one of these conductivity apparatuses, and we're going to actually do this real instead of just talking about the picture. If I hook up a battery to a light bulb and then two electrodes, and I just put them in water, the light bulb is not going to light up because the water cannot carry the charge of the electricity. Electrical current is negative electrons moving. And so nothing will happen, but then if we add table salt, now the salt is dissolving and forming ions that are separate from each other that can move around, and so those ions can carry the electric current, and the light bulb goes on. So that's what happens with an electrolyte. A non-electrolyte does not conduct electricity. So you put sugar into this beaker, and the sugar dissolves, yes, but it doesn't form ions, and so it can't carry electric current. So this is a non-electrolyte solution. And that is the case with most molecular compounds. They remain molecules and they don't conduct electricity. So you've probably heard about electrolytes in everyday life, right? Like Gatorade, Powerade, etc. If you're out there, a football team, practicing, and it's 106 and you've got all those pads on and stuff, you're sweating like a beast, and you're losing a lot of salts in your sweat, which if you ever let a sweaty shirt dry out, you probably saw it had like white crusty stuff on it, right? That's the salt that came out of your body. Yeah. So that needs to be replaced. We're not talking here about, I walked across the parking lot and my forehead's wet, right? We're talking about lots of sweat. You lose electrolytes, and so you need to replace them. And so that's where these various electrolyte drinks come in. They have salts in them, not just sodium chloride, but they'll have magnesium and potassium and different things, hopefully in the correct ratio that your body needs. Yeah?
Do you lose potassium too when you sweat?
Yeah, you lose potassium also. You lose a whole bunch of different
Vomit
things.
a lot.
Yeah. Yeah, and vomiting, that's another time, especially small children,
Yeah.
they'll get an illness where they're
Dehydrated.
like vomiting and they have diarrhea. I mean, literally nothing is staying in their body, right? So then they're losing a lot of these salts. And those electrolytes are very important inside your body. It's how your nerves communicate and your body functions because of all of these different ions in your body. And so those ions drop too low and then your organs stop functioning. So it's really important to get those replaced.
Yeah. Last time I thought it was just the salt that you were losing. I was like other stuff too, like that.
Yeah, so when you say salt, you mean table salt.
Yeah, table salt. Right?
Yeah. When I say salt, I mean ionic compound. Yeah. So it's true. You're losing salt, but it's a broader category of things. Yeah. Anybody have any questions about that? Do you need the sugar and the flavor in the Gatorade?
Yeah.
No.
I ain't drinking it without it.
Well, she says yes. I'm not drinking it without it. Well, that's the truth. The sugar is not helping you rehydrate at all, and the color's not doing anything.
But I need it. The blue.
Oddly enough, for Gatorade, it's doing something because when it's like sweet, it means that you're fully hydrated.
Oh,
There's
interesting.
a chemical marker in it that.
And if
like,
it doesn't taste sweet, then
well,
you're
actually, yeah. When it doesn't taste sweet, it means you're fully hydrated. If it does taste sweet, it means you're lacking.
interesting.
Let me go taste it.
I hadn't heard that before.
Okay. No,
I
you
know.
probably are.
I think a lot of us do
We don't
spend
realize
most
it.
of our lives slightly dehydrated.
We don't
When
realize
when
it.
you go and use the toilet, it's not supposed to be yellow.
And it's not supposed
Right.
to be crystal white either.
No, it should be just very, very pale yellow. And if it isn't, that means you're not drinking enough liquids. And that can affect all kinds of things, including the ability to learn. So yeah, make sure you guys are all hydrated.
Yeah.
This is showing the interactions between water molecules and sugar molecules. Sugar molecules also have a lot of oxygens and hydrogens, and here these oxygens and hydrogens aren't sharing their electrons equally either. The oxygens always hog the electrons. And so this oxygen is going to be a little bit negative. Well, actually, it is, but the line doesn't point to that one. No, this one. This one's a little bit negative, and so the positive hydrogen end of a water molecule is going to be attracted to that. We have these slightly positive hydrogens, the slightly negative oxygen of the water molecule is attracted to that. And so the water molecules are going to do the same thing to the sugar molecule. They're going to come and surround it and make it feel comfortable so that it can leave the rest of the sugar and go off and dissolve in the water. And we can't see it anymore because these particles are too small to even deflect light. So it looks like they've disappeared, but they've just separated into individual molecules. The reason this is a non-electrolyte solution is because this molecule is staying intact. There are no positive and negative ions that can carry the charge. We learned that acids are molecular compounds that form ions when you put them in water. So you put HCl into water, we call it hydrochloric acid now. It separates into hydrogen ions and chloride ions. That looks like an electrolyte, doesn't it? There are charged particles that can carry the electric current, and acids are electrolytes. We have two categories of acids, strong ones and weak ones. And this has nothing to do with how caustic or dangerous they are. It just has to do with the relative amounts of molecules that turn into ions. In a strong acid, all of those molecules become ions. HCl is a strong acid, And so when you dissolve it in water, there aren't any HCl molecules hanging around. It's all hydrogen ions and chloride ions. In a weak acid, it only ionizes a little bit. So here's a picture illustrating acetic acid, which is really not the best illustration because it's kind of hard to see the difference between these. But here we have an intact acetic acid molecule. Here we have an acetate ion and a hydrogen ion. So that one has ionized, but most of them have not. So will this conduct electricity? Yes, but not very well. So we've been using arrows that just point from reactants to products, but now we'll also sometimes see these double-headed arrows. And what this means is this goes in both directions. This is not going completely to the right. It's an equilibrium, if you remember from Chem 3A. So for weak acids, most of the molecules remain intact and only a few of them ionize. So strong electrolytes dissolve completely into ions, like strong acids do. So strong acids are strong electrolytes as well as soluble ionic compounds, and these solutions conduct electricity well. Weak electrolytes are going to be mostly molecules, only a little bit ions, and that would include the weak acids, and they conduct electricity weakly. Not every week, but not very well. The strong weak makes a little more sense when you look at the light bulbs. So here we've got a strong glow from this light bulb, right? And this one is weak, and that one's not glowing at all. This is a weak electrolyte. There are some ions here, enough to let the current flow, but not as many as over here, where we get a good current flow. And in the sugar solution, there's no ions, and so no current will flow. Any questions? Which aqueous solution conducts electricity? What the heck, right? Okay, you have the information to answer this question. You have the knowledge. We learned how to recognize ionic compounds and acids and molecular compounds, right? Which of those compounds can conduct electricity when dissolved? Acids and ionic compounds. Molecular compounds cannot. So let's look at these one by one. KBr, is that ionic?
Yes.
Yeah, because potassium is a metal. So will this conduct electricity? Yes, it will. C6H12O6, is that ionic? No. Is it an acid? Doesn't start with H. It's not an acid. This is actually a sugar. Not going to conduct electricity.
Glucose, right?
Well, yes, it could be. There's actually, it's a hexose. There's actually a whole bunch of sugars that have exactly the same chemical formula.
Different structure.
Different structures. Yeah, glucose is one of them. And so that one's a no. What about this guy? Is this an acid or an ionic compound?
Acid.
It's so tempting to say acid because there's this hydrogen just taunting you.
Oh, it's
Hydroxide.
OH.
But it's at the end, right? If it was an acid, the hydrogen would come first.
Something like acetic acid or-
Right, it kind of looks like that. So in Chem 1A, we are very careful in how we write our chemical formulas, so that acids always start with an H. So I would never write this starting with an H because that would be confusing, and I wouldn't expect you to know just that this was not an acid. This is where we sometimes run into problems when we look for answers on the internet. Because in different fields of work or study different sciences, some of these chemical formulas are written in different ways. And so when I'm looking at your answer, I can tell when you Googled it because it looks ridiculous according to the rules we've learned in our textbook. Okay? Yeah, there are people that write it that way, but they're not chemists, right? And they're certainly not Gen Chem students. So this is tempting to call an acid because it's got this hydrogen hanging out there, but the hydrogen has to be at the front for this to be an acid. And so that is not an acid, it's not ionic, it's not going to conduct electricity. When an ionic compound dissolves, it forms ions. But not all ionic compounds will dissolve in water, which is good, because much of the Earth's crust is made up of ionic compounds, and if they all dissolved in water, it would just be a big bunch of soup here. So we talk about compounds being soluble or insoluble. Soluble means it dissolves in water. Insoluble means it does not. Now the thing is, nothing is absolutely insoluble, because that would mean that not even one ion came off, because if one ion comes off, then it dissolved a tiny, tiny bit, right? So the truth is that even insoluble compounds dissolve a little tiny bit, but we're going to ignore that until Chem 1b, okay? So we're just going to think that they don't. But I just told you the truth, they actually do. So when ionic compounds dissolve, the anions and the cations separate from each other. This isn't called ionization because they were already ions, but it's called dissociating because they're moving away from each other. So this is an ionic compound, Na2S, and so what happens is all these ions are going to separate from each other. So this formula had 2 sodiums, Na2, so there are 2 sodium ions, and there's 1 sulfide ion, and we write all the ions separately. If you have a compound with a polyatomic anion, like sulfate, well, that sulfate stays together. The sulfate ion is going to float around as this, fancy ion, and the sodiums are going to be just their own little sodium selves. So in Chem 1a, when we have an ionic compound like this that dissolves, it's going to form 2 kinds of ions. 1 cation, 1 anion. So it's tempting for some students to say, well, sulfide and 4 oxides, and no, it doesn't do that. So if we look at silver nitrate, so here we have silver and nitrate, 2 ions, 1 is silver, 1 is nitrate. These dissolve in water and form a strong electrolyte solution. They all separate very nicely. But silver chloride is almost completely insoluble. And so if you looked at an illustration of that, we've got silver and chloride ions, and they're all just like super into each other. And they're like, water, not today. Won't dissolve. And you can stir this and stir this and stir this, and it will not dissolve. Why does silver chloride not dissolve and silver nitrate does dissolve? It's complicated. That's my best answer. There are a lot of different factors. This is not one of those things that you can just look at the periodic table and miraculously get all the answers that you want. Sorry. So we have a set of empirical rules. So people did experiments. It's like, well, here's this, sodium sulfate. Let's put some in water and stir it up. Yep, that one dissolved. Okay, let's try a different one. And lots of people did this, and they actually measured how much would dissolve and stuff, but everybody's experimented with this. And so then they try to make some sense out of which ones dissolve and which ones don't. And so that leads us to a set of rules,
We don't like rules.
solubility rules. This looks way more complicated than it is. So, in the past, I have made students memorize this. I'm not going to make you memorize it, but you do have to know how to use this table. Okay? So the way you use this table is you start at the top. The top section, compounds with these ions are generally soluble. The exceptions are listed over here. So you start at the top and you find your ions. So, let's say we're doing sodium chloride. Well, there's sodium ion. Sodium compounds are soluble with no exceptions. Doesn't matter what the other ion is. It's going to be soluble. So we could stop looking at the table. What if we were looking at like lead chloride? Right? Well, then we didn't find lead or chloride here. We don't find lead or chloride there. Oh, here's chloride. Chloride compounds are generally soluble unless they're with silver, mercury, or lead. Lead chloride, insoluble. And I'm done. We're not going to look at any more of the table. So you start at the top and you work your way down. When we get to the bottom, these guys are generally insoluble. So when we look at the exceptions over here, we actually don't really need most of those exceptions because if we start at the top, we won't ever get there. Because hydroxides, lithium, sodium, potassium, and ammonium hydroxides are soluble. Well, that's those guys. If I was doing sodium hydroxide, I'd never get down there. So what I like to do is just get rid of that. It just makes it look more complicated. And then with the sulfide, calcium, strontium, and barium are soluble. Hydroxide with calcium, strontium, and barium, slightly soluble. Let's just say those are the exceptions. Down here, carbonate and phosphate. Most of those compounds are insoluble unless they have those guys. Again, we didn't need that rule because if we start at the top, we're never going to get there. And the exceptions in the top, here we've got strontium, barium, and calcium, just like the exceptions down here. Lead and silver, those are the same as those guys up there. So lead, silver, mercury, calcium, barium, strontium. So I would encourage you, as you need to predict whether compounds are soluble or not, to think about it first and then check it in the table. Because it is a lot easier if you can remember, well, ammonium compounds are always soluble, so I don't need to go look at the table. So we should be able to answer questions like this. Predict whether each compound is soluble or insoluble. Nickel sulfide. So we're going to go to the table here, and we're looking for nickel. Let's write those down. We're looking for nickel ion and sulfide ion. So we go through the top, not seeing any of those. I get here, sulfide. So sulfides are generally insoluble, and nickel is not one of the exceptions. So nickel sulfide then is not soluble. It's not going to dissolve. Insoluble. Magnesium phosphate. And we need to be able to look and identify what are the two ions that I'm dealing with here. I've got magnesium ion and I've got phosphate ion. So again, we're going to go back to this chart and we're looking for magnesium and phosphate. Nope, 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 nope. Oh, there's phosphate. Magnesium and phosphate is not an exception. Magnesium phosphate, not soluble. Lithium carbonate. Do you remember what that first row is? It's the 1A metals. It's lithium, sodium, and potassium, and ammonium. So if this has lithium in it, all lithium compounds are soluble, no exceptions. So that's going to be soluble. And then this one, now this is that one that's a little bit tricky. It's not just the first element is the first ion. Ammonium, NH4+, and chloride. And again, this ammonium is in that first row of always soluble, no exceptions. So this one is soluble. Any questions?